Okay, welcome back for lecture 2 in unit 3. In this lecture, we're going to talk about the steps to take magma and form it into an igneous rock. In particular, we're going to talk about its origins, the different locations where magma occurs and where it goes. And then we're going to talk about the texture or the appearance of those igneous rocks. Okay, so first up, when we think about magma, when we think about that molten rock inside of the earth, one of two things can happen. First, as we have talked about, that magma can go up to the surface in the form of a volcano. Volcanoes oftentimes have a magma vent that is connected to a magma chamber deep down in the earth. Once that magma follows that vent up to the surface, it is able to then exit onto the surface, and we call that molten rock lava. Once it reaches the surface, then we call it lava. Once it is still in the ground, it is still considered to be magma. This process of lava coming out onto the earth, we give it a term called extrusive. It extruded onto the surface of the earth. Um, at the surface of the earth, that rock is susceptible to conditions that are very unlike the magma chamber that it was once in. Namely, it is a lot colder on the surface than it is deep down within the earth. And so it's going to start cooling down almost instantaneously, almost rapidly, very rapidly. And because its cooling process is so quick, it does not have time to grow nice, large minerals. Minerals take a long time to grow. Remember that video in our unit on minerals where we watched the minerals precipitate in that solution. They didn't grow very fast. It took them a long time to grow. It takes minerals even longer to grow inside magma chambers because there's a lot of stuff that the atoms need to move through to get to their sites for mineral growth. So once a lava flow or lava makes it to the surface, it is under cold temperatures, and so it cools down very fast, and those minerals do not have any time to grow. Here's the second option. What happens if that magma doesn't go onto the surface? Let's just say it's totally cool, just chilling inside the earth. Well, it's not chilling, it's actually staying warm for a longer period of time. So for that, we still call it magma. Oftentimes its location is called a magma chamber. That magma chamber is give it a term called an intrusive magma chamber because it's oftentimes intruding into other layers of the earth. And because it's deep down in the earth and surrounded by rock, the heat does not have anywhere to go very quickly. It's very insulated. And so, like the consequences is that the magma changes temperature very slowly. It cools down very slowly as it is inside the Earth. This slow cooling um, creates is a sufficient amount of time to create really large minerals. So we got big minerals being grown inside the Earth, whereas tiny minerals for things that are on the surface. Now, a lot of this takes a lot of time, and there are volcanoes that we can go and look at and study this process, but oftentimes we will see igneous rocks long after they have formed. We will find them at this last stage. We will find igneous rocks with tiny minerals, and we will find igneous rocks with big minerals. Just on that information alone, tiny or big, we can infer where these rocks have come from. Did they form inside the earth in a magma chamber and grew over a long period of time, or were they part of a volcanic eruption that left them on the surface to cool very quickly and form no minerals? So these are very helpful pieces of information by looking at the size of the minerals. Here's just an example of that. On the left side, we see a phaneritic texture meaning the size of minerals. And phaneritic comes from the Greek word, a Greek root to see with the eye. And so these minerals are very large. We can see whole minerals, black minerals, white minerals, is quartz, biotite, feldspar, very large minerals that we can see. These large minerals indicate to us that they had a long time to grow. They cooled down slowly over time, most likely in a very large magma chamber. On the right side here, we see aphanitic, coming from the root being unable to see. We have a hard time making out individual minerals. There's sort of this like dusty or peppery look. Maybe I can point to a spot, but overall, those minerals are super tiny. I can't really see them well at all. This is a characteristic of igneous rocks that cooled very quickly at the surface, most likely through a volcanic eruption. So here's just two examples with those key terms related to the texture or the size of the minerals. Here's just some more examples I want you to see. The same two that we just saw for the phaneritic texture, meaning coarse grained minerals or the fine grained minerals. And then there's some in between. So this is still phaneritic, but it's sort of a medium grained minerals, smaller than the one on the left, but definitely larger than these aphanitic textures. And then Earth can always throw us a curveball. Porphyritic texture has both very large minerals and very tiny minerals. What this implies that is that the cooling was in the magma chamber was going very slowly, and then some process, maybe the mixing of two magma chambers or the sudden eruption of that magma chamber, caused the cooling to speed up and could cool down very quickly. So we go from a coarse to fine formation in these minerals, a slow then fast cooling process. And then here's just some examples of the microscopic views of these minerals. For those aphanitic pictures, the ones that we can hardly see at all, if we look at them under a microscope, we do see those minerals. They're just incredibly tiny. Whereas the phaneritic textures, those have a very large individual minerals surrounded by other very large minerals. Here's the porphyritic, very large minerals surrounded by very small minerals. This indicates that there's two stages to the history of that magma. It was cooling down slowly to form the large crystals, and then some process, maybe the mixing of a cooler magma with this hotter one, caused things to start to cool down much faster. Couple more textures to keep in mind. Glass is an indication that the magma was, or the lava was cooled instantaneously. There is time for no minerals to form, and everything is sort of stuck solid as it was in the magma chamber. Pyroclastic is a texture that is created by the explosive eruption of magma, of lava onto the surface. And it sort of creates a deposit of that lava that has been thrown and moved to a new location. So it's composed of previously rocks that pre-existed that eruption and are incorporated into the new lava or ash that has been sent out. And then finally, there's the pegmatitic or pegmatite texture. And this is some very, very large. These are usually the last minerals to form inside a magma chamber. We have some giant feldspars here and some giant micas. And then here's the size of some people, just for an example. These are incredibly large minerals that have taken an incredible long amount of time to form.